Today we're covering 15.1 derivatives of trigonometric functions. So in general, I'll just dive right in. When you differentiate sine x, what you get is cosine x. Cosine always a special one. When you differentiate cosine x, what you get is negative sine x. So in a very quick nutshell, if y is equals to sine of x, differentiating y with respect to x will give you cosine x. Similarly, if y is equals to cosine x, differentiating y with respect to x will give you negative sine of x. Then the third one that we need to know about is tangent x. So if you differentiate tangent x, differentiating y with respect to x, what I get is secant square x. Just a little bit about notation here. When you have secant square x here, it simply means, right, that what we have is secant x times secant x is actually secant x bracket square, the notation that we write it is in this way, secant square x. Okay, please be careful, this is not the same as secant x square. Make sure you know the difference between this and this. Okay, very quickly, based on what we have learned so far, I will give you example 1 and then you can try 1. So for example 1, what we do here is part A. If I am attempting to differentiate with respect to x, 3 sine x minus 2 cosine x, this works the very same way. As we said, sine x, you differentiate, it becomes cosine x. Now, cosine x, you differentiate, it becomes negative sine x. This negative and this negative will interact to give you positive. That is why this becomes positive 2 of sine x. Part B. Part B, be careful. What we have here is this. Notice that this is one function multiplied to another function. So what we have learned in the past with the product rule will apply here as well. If u is equals to x squared, differentiating u with respect to x gives you 2x. If v is equals to cosine of x, similarly, differentiating v with respect to x gives you negative sine of x. So if I were to apply my rule, so I differentiate with respect to x squared cosine x, v du dx, I get 2x cosine x plus u dv dx. U is x squared, dv dx is negative sine x. I just simplify everything. Positive and negative will give me negative here. So this gives me negative x squared sine x. I move on to C. Okay, for part C, what we actually want is, notice that they would like us to differentiate tangent x over x plus 1. There is a function in the numerator and denominator. So what we need to do is actually to apply the quotient rule. So u is equal to tangent x. Differentiating u with respect to x is secant square x. Similarly, v is equals to x plus 1. Differentiating v with respect to x is equals to 1. So v times du dx is secant square x minus u. Okay, I'm running out of space here. Let me just shift everything down. Minus u. U is tangent x times dv dx, which is 1 over v squared, which is x plus 1 squared. And I'm done with example 1. If you can, please quickly pause the video and try 1. Okay, try these questions now. And I will unpause and then unpause the video and we will continue. Now I'll show you the answers to try 1 itself. So try 1, I am differentiating with respect to x minus 2 sine x. So differentiating x will give me 1. Sine x differentiated will give me cosine x. So I get is 1 minus 2 of cosine x. That's it for part A. For part B, this is once again an issue about the product rule itself, x plus 1 is u, tangent x is v. So u is equals to x plus 1. Differentiating u with respect to x gives me 1. V is tangent x. Differentiating v with respect to x will give me secant square x. Hence, for part B, if I'm differentiating with respect to x, x plus 1 tangent x, what I'm getting is v times du dx tangent x times 1 plus u, okay, which is x plus 1 times secant square x. You can leave the answer as this, it's perfectly fine. Part C. Part C is clearly a case of the application of the quotient rule itself. So u is cosine x. Differentiating u with respect to x is negative sine x. V is x. Differentiating v with respect to x is 1. Hence, for part C, if I differentiate with respect to x, cosine x over x, v times du dx is negative sine x minus u, which is cosine x, times dv dx is 1 over v squared, which is x squared. So I get negative x sine x minus cosine x divided by x squared. And this is it. You can leave it as such. The answer in the book actually goes on to actually goes on to take out the negative sign, but just leave it like this, or they factorize negative 1 from the numerator, but I think this is perfectly fine. So now the thing here is this: what happens if it's not sine x? For example, in example 2, instead of having just differentiating sine x, now is sine of 3x plus 2. So this is similar to what we have learned before. If you differentiate the sine, it becomes cosine of whatever is inside the bracket. Then you need to multiply and with the differential of what is inside the bracket with respect to x itself. So as I'm going to show you later, when you differentiate sine of 3x plus 2, you differentiate sine, it becomes cosine. You copy out the 3x plus 2. What is required is that you will also have to, I don't know why we went back so far. What you also have to do here is to differentiate the bracket itself. Okay, and this applies for cosine and also for tangent itself. It's no worry. Why don't we just go through some of the examples first? So, if I'm differentiating with respect to x, sine 3x plus 2. So if we remember, differentiating sine gives me cosine. Copy out the bracket, 3x plus 2. Now, you have to differentiate what's inside the bracket. 3x plus 2, you differentiate with respect to x, you get 3. So you put the multiply the entire term to 3 there. Similarly, for part B, what we have is cosine of 2x minus pi over 3. Differentiating with respect to x, cosine gives me negative sine of 2x minus pi over 3. If you differentiate the bracket, what you get with respect to x, what you get is 2. So I'll just shift my negative a bit over here and put the 2 in front there. That is from what was inside the bracket itself. Part C gives me tangent of pi minus x over 2. And if I'm trying to differentiate this term here, d dx, again, differentiating tangent gives me secant square pi minus x over 2. If I were to differentiate what was inside the bracket, pi differentiated with respect to x gives you 0. Negative x over 2 differentiated with respect to x gives you negative half. So I will plant my negative half in front of the entire term itself. And last but not least, okay, what we have here is sine of x to the power of 5. So I'm differentiating with respect to x, sine x to the power of 5. So sine differentiated gives me cosine x to the power of 5. What's inside is x to the power of 5. You differentiate, you get 5x to the power of 4. So I'll plant 5x to the power of 4 in front of the whole term itself. And that is that for example 2. I urge you now to pause the video and try to consolidate your learning. And once you're ready, you may unpause the video and I will carry on with the answers to try 2. Try 2a, I am differentiating with respect to x, sine of 3x. Sine, you differentiate, gives me cosine of 3x. I differentiate what's inside the bracket, I get 3. So it's 3 cosine 3x. Similarly, if I'm differentiating with respect to x, cosine of 3x plus 2, cosine gives me negative sine of 3x plus 2. I differentiate what's inside the bracket, I get 3. So let me just shift my negative sign a bit and I put here negative 3. Part C, I'm differentiating with respect to x. Tangent of 4x minus pi over 3. Immediately what I get is secant square 4x minus pi over 3. I differentiate the bracket, I'm left with 4. So I get a 4, I put it in front there. 4 times secant square of 4x minus pi over 3. And that's it for try 2. Now we are moving on. So in general, as what I've shown you earlier, when you differentiate, then you have to also differentiate what was inside the bracket and put it out in front. Okay, similarly, all right, I will show you example. I'll show you now another example whereby we have this. Okay, this is application of the chain rule. So if you remember the chain rule, for example, if I have x squared plus 1 to the power of 5, I'm differentiating this. I will take the product of the power of the index is 5, x squared plus 1, reduce the power, 5 minus 1 is 4. I differentiate what's inside the bracket, I get 2x. So I will get 10x, x squared plus 1 to the power of 4. When you work with sine, it's also the same thing. For example, in example 3, I will do A on this page and I follow on. Sine 5x actually means sine x to the power of 5. So that means when I'm differentiating with respect to x, sine 5x, it works the same as the chain rule itself. So what I'll do is the power will be brought down and you multiply it to the term. So it's sine of x. So the power, you will minus 1. 5 minus 1 gives you 4. Then you differentiate inside the bracket. What I have inside here is x. You differentiate is 1. So this is my final term for A. When you differentiate sine x to the power of 5 or sine 5x. For part B, what is happening here will be the same thing. So what I'm doing is I'm differentiating with respect to x, 3 plus tangent x cubed. So the power comes down, 3 plus tangent x, power minus 1, 3 minus 1 is 2. Tangent x differentiated will give you secant square x. I simplify, I get 3 secant square x, 3 plus tangent x squared. Now for part C, okay, part C might be slightly convoluted, but we can do this. Just pay attention to what we're doing with part C. So what we have here is cosine of 2x. This is power of half. Okay, slowly. This one will be first the half. We bring down the power, so we get half here. Then we are left with 2 minus cosine of 2x, then power negative half. This power half minus 1 is negative half. We still need to differentiate what's inside the bracket. Negative cosine, okay, cosine differentiated gives you negative sine. So negative cosine differentiated gives you positive sine of 2x. But Don't forget that when you differentiate this, you also have to differentiate the 2x, so you have to put a 2 down here. So if you try to simplify, half times this will give me sine of 2x divided by square root of 2 minus cosine 2x. And that is it for part C itself. Then I'm going to move on to try 3. Please take a moment now to pause the video and attempt try 3, and I will go through try 3 in a very short moment. For A, I'm differentiating with respect to x, cos cube x. First, the 3, we multiply it to cosine of x. The power must be reduced by 1, so it's cosine square x. You differentiate what's inside the bracket, you differentiate x, it becomes 1. So this is my final answer for part A. For part B, I'm differentiating with respect to x, tangent x minus 3 to the power of 4. First, I bring down the power 4, tangent x minus 3, the power 4 minus 1 is 3. Don't forget to differentiate what's inside the bracket. Tangent x differentiated is secant square x. Hence, I get 4 secant square x multiplied to tangent x minus 3 cubed. Part C. Part C, what I'm attempting, I wrote C twice. What I'm attempting to differentiate is to differentiate 1 minus sine x plus pi to the power of half. So power bring down, so I get 1 minus sine x plus pi. Half minus 1 gives me negative half. Then what I will need to do is to differentiate what I have inside the brackets here. So 1 differentiated is 0. Negative sine x plus pi differentiated gives you negative, no change in sign, cosine of x plus pi. Just like this. So if I were to simplify everything, what I get is negative cosine x plus pi is in the numerator, negative cosine of x plus pi divided by 2 times of square root. I am actually expressing this in positive index, so 1 minus sine of x plus pi in my denominator. And I am done with try 3C. Okay, one final example for this 15.1 and we are done. Okay, for 15.1 we have example 4. So example 4, we are going to use these trigonometric functions and their derivatives to solve what we've already solved earlier. For example, in our maxima minima problems and for our stationary points as well. So, for example, a curve has the equation given by y equals to sine x minus 2 cosine x. Find the coordinates of the stationary points of the curve. So if you remember, what we are aiming to solve is dy dx is equals to 0. So without much further ado, y equals to sine x minus 2 of cosine x. I solve dy dx. Sine x gives me cosine x. Negative 2 cosine, it gives you negative, cosine differentiated, it gives you negative sine. So here is plus 2 of sine x. For a stationary point, dy dx equals to 0 for stationary points. Hence, cosine x plus 2 sine x is equals to 0. Very quick recap, okay, of how to solve this. 2 sine x is equals to negative of cosine x. Dividing both sides by cosine x, I get 2 tangent x equals to negative 1. Tangent x equals to negative half. I hope you remember how to solve this because for this, tangent is negative. Now, ASTC, A will occur here. in second quadrant, T is positive, and C as well in the fourth quadrant. Now to find alpha, okay, or my reference angle, I take inverse tangent of half. Please be careful, these values should be in terms of radians, and I find that my alpha value is 0.46365. That's my alpha value. Then, okay, since I know that it's in my first quadrant and my second quadrant and my fourth quadrant, my angle x is equals to pi minus alpha and 2 pi minus alpha. So my x values in this case should give me 2.68 and 5.82. Okay, which is this value and this value down here. Now I have the two values of x. In the second part, what they want me to find is the using the first derivative test to determine the nature of each stationary point. So a very quick recap. I know we can't flip this like a book. So dy dx in this case, what we had was cosine x plus 2 sine x. Now to use the first derivative test, what we do is we draw our table. Okay, then what we have is x sine of dy dx. Then we have the tangent. What does the tangent look like? And finally, we have the sketch itself. So now we have 2 points. One is where x is 2.68. Then not forgetting that we have another point, okay, where my x value and the other point in my x value is 5.82. So now if the first derivative test, 2.68 plus 2.68 minus, if you key in the sign of dy dx, this is positive, this is negative. So what you get is this one. Okay, so I say that at x equals to 2.68, what we have is a maximum point. Similarly, for 5.82 plus and 5.82 minus, what I will have is a point like this, and this one at x equals to 5.82, what I have is a minimum point. Now, what they have asked in this question is to find the coordinates. So in order for me to find the coordinates, don't forget that the equation is y is equals to sine x minus 2 cosine of x. So ensure that your calculator is in the correct mode. I plug 2.68 into x over here. What it will give me is y is equals to 2.24. So that means at 2.68, 2.24 is a maximum point. Similarly, if I plug in my x value into y over here, what I should obtain is y is negative 2.24. So 5.82 negative 2.24 is a minimum point. So this is how we mesh what we have learned in the earlier chapters with this current chapter. And that's it for the video presentation for 15.1. Please go try out the questions. Thank you.